Hello and welcome to the last part of your EEE 157 Lecture 11 on bit error rate analysis. Without further ado, in this part, we will be talking about the bit error rate itself, how to analyze the bit error rate of your pulse amplitude modulation. Only for PAM, and for the other digital modulation techniques, I'll just show you the theoretical bit error rate curves. Okay? So first things first, how do we calculate the probability of bit error? Again, the probability of bit error, which is also the bit error rate, is used to evaluate the performance of a digital communication system. The lower the bit error rate, the better your digital communication system. So for some preliminary, we will assume that for our digital modulation techniques here, we will assume that the gray code mapping is used. Okay? And from there, assuming that gray code mapping is used, we can compute the probability of bit error quite simply using this equation right here. Let's break that down. I know it looks complicated, but let's break that down. Okay? So your probability of bit error, okay, is equal to 1 over b. B here is the number of bits per symbol. And within the summation, there are two expressions. The probability that your symbol I is going to be transmitted multiplied by the probability of error given that SI is transmitted. Okay? And you sum all that for all possible symbols in your constellation. Okay? So this is the formula for the probability of bit error. So what you do here is that you get some symbol S sub I and analyze the probability of error for that specific symbol. Do that for all symbols and then apply it here in this summation. It sounds tedious. Yes, it is actually tedious. Okay? But you will see a pattern when you try to analyze it. Okay? So for more complicated digital modulation techniques, we will leave that to your higher courses if you're gonna take higher courses. Okay, oops. Right. So more comments on that. So the probability of bit error is equal to 1 over b. B is related to the number of symbols in your constellation through this formula right here. So b is equal to the logarithm of m base 2, where m is the number of bits per symbol. Sorry, the number of symbols in your constellation rather, and b is the number of bits per symbol. Okay, so let's look at a special case. Okay, the most probable case, it's reasonable to assume that your constellation is equiprobable. The symbols of your constellation is equiprobable. So the probability of any symbol S sub I is constant, equal to 1 over m. So each of them, all symbols, have a probability of 1 over m occurring. Okay? That means we can simplify, if we combine all these, we can simplify the expression to the probability of bit error is equal to 1 over m times the logarithm of m base 2 times the summation of the probability of error given some symbol S sub I is transmitted for all I in your symbol space or your constellation. Okay, so that's how you break down that formula that you see here. So it looks complicated at first, but when you analyze it, it's actually easy to understand. Okay, so the Q function here is used to express your bit error rate. Since we're talking about probability distribution functions, and we're talking about the probability that your noise exceeds some threshold value, x, there's no closed form expression for that. You try to integrate your Gaussian function, it's actually, there's no analytic expression for that. So we can use q of x instead to express this integral. Okay? So what q of x is, just some observations. As x increases, the integral of q of x, or sorry, the integral of your PDF q of x decreases. Okay? So this makes sense, since if you look at the Gaussian distribution, you set a threshold x here. Okay? So this is the integral of your distribution from x to infinity. If you increase x, then the area of your distribution decreases. Okay, the area that you are interested in decreases. So this is one property of your Q function. It's always decreasing. Okay, so we will use then the Q function to express the bit error rate of your 2PAM constellation. So let's do that here. So the constellation map is useful in this case. So what we do with the constellation map is that we assume that one symbol is transmitted. In this case, let's say it's negative D. And we overlay that Gaussian distribution all over negative D. At negative D will be the mean of your distribution. So any point here on this curve for your Gaussian distribution represents all the possible values of the received symbol given that negative D is transmitted. So if your symbol is here, then the received symbol is negative D plus N. And N can take any values. But there will be an error if N exceeds this value right here. And the distance between this boundary and negative D is equal to D. So we assume here that the boundary, the decision boundary between negative D and positive D is at the midpoint between them. Okay, so when N exceeds this threshold, then we have an error occurring. So what's the probability that N is greater than the threshold D? So let's look at that. So recall that the probability distribution function, or the PDF of your normal distribution, is equal to 1 over pi, square root of pi n naught times e to the negative n squared divided by n naught. N naught here, recall, is your power spectral density. More accurately, n naught over 2. Okay, so the probability of error given negative d is transmitted, so we get the area of this part of the curve. Okay, and that is equal to this expression that you see here at the bottom. You integrate this this PDF from d to positive infinity. Okay, by using a change of base, you can show that this expression is equivalent to q of d times square root of 2 over n naught. Okay, so that's how you get the expression for the probability of error in terms of the q function. Okay, we do the same analysis assuming positive d is transmitted. Okay, the distance between the boundary and positive d is equal to d again. Okay, and the probability of error occurs when n is less than this value right here. So we have the symbol at this point here is when you have positive d plus n. Okay, if n is less than negative d, then an error occurs. So we get the probability of this happening, which is the integral from negative infinity to negative d. So that's the bounds in this integral. And actually, this area is equal to the area that you got earlier. So invoking the symmetry of the Q function, we get the same expression for the probability of error given positive d is transmitted. So now we have the probability of error given both signals are transmitted, given d is transmitted, and given that negative d is transmitted. We can now compute for the bit error rate, or the probability of bit error, for your 2PAM constellation. Okay, so again, they're equiprobable. Then the probability of positive d being transmitted is 1/2. The probability of negative d being transmitted is positive 1/2, is 1/2. Okay, and we add that, since these two are equal, then we can see that the probability of bit error is equal to the q of d times square root of 2 over n naught. Okay, this is not yet complete. We want to express this in terms of the SNR per bit. Okay, again, the SNR per bit is a fair metric to compare your different constellations. Okay, we look at the effect of the noise on the bit level, not the symbol level. Okay, so recall that D is related to the energy of your 2PAM constellation. D is equal to square root of E sub B. Okay, substitute that, we get this expression, final expression for your probability of bit error. Okay, So some notes, if there is no signal, when EB over N naught is 0, when there's no signal, the probability of bit error approaches 1/2. So if EB over N naught is 0, then Q of 0 is actually equal to 1/2. How did that happen? Well, if you look at your probability distribution function, okay, if you set your threshold at 0, knowing that this is symmetric, then the area of this is equal to the area of this. And we know that since this is a probability distribution function, the total area of your distribution of this distribution is equal to 1. So if we cut that in half, then the area of this is 1/2. The area of this is also 1/2. So the function when Q, if the argument is 0, is equal to 1/2. Okay? So the worst case scenario here, when there is no signal, is that your probability of bit error is equal to 1/2. Okay? Oops. So the probability of bit error here is equal to 1/2. So it's not the worst case scenario if the probability of bit error is 1. If the probability of bit error is 1, then you just invert the bits, you get the probability of error equal to 0. The worst case scenario happens if you're purely guessing what bit is transmitted given your observation. Okay? So in this case, you don't observe anything because there's no signal. So you're just guessing what bit was transmitted. Okay? It's like guessing what another person is saying when you can't hear them. Okay? If you know what they're saying, then maybe you can read their minds. But anyway, that's a different story altogether. Okay? So the worst case scenario for any communication system, for a digital communication system, is that the probability of bit error is 1/2. This is the time when you are purely guessing what is the bit transmitted. Okay? Okay. So we can plot the probability of bit error given your signal to noise ratio per bit. So we can plot that. We can see that the BR decreases as EB over N naught increases, which makes sense. Since if you have a higher signal to noise ratio, that means your symbol constellation is less corrupted, okay? And you have less probability of your noise corrupting your symbol detection. Okay. Okay. So now let's look at 4PAM. We will use the same approach as 2PAM, where we assume some symbol is transmitted and then overlay a Gaussian distribution for that. Okay? So let me just fix this. So for 4PAM, let's assume here that negative 3D is transmitted. We overlay the Gaussian distribution. Okay? So as you can see, there will only be an error if your noise crosses this threshold. Okay? And the distance between this boundary and negative 3D is equal to D. So again, this is just the probability when N is greater than D. Okay? So the probability of error given negative 3D is transmitted, which is also the probability of error when positive 3D is transmitted. They're the same. Okay? You get this expression for your probability of error. Okay? Let's examine when negative D and positive D is transmitted. So due to symmetry, again, due to the symmetry of the problem, it's the same probability of error when negative D or positive D is transmitted. Both of them have the same probability of error right here. So in this case, there are two sides to your probability of error. Okay? There will be an error when N exceeds positive D on this side, and there's also a probability of error when N exceeds or becomes less than negative D, and that's the area of this side. And due to the symmetry again of the problem, then the probability of this occurring is equal to the probability of this occurring. Okay? So this is just the same expression as what we got earlier here. But in this case, since these two are equal, the probability of error given negative D or positive D is transmitted is equal to twice the probability of error of negative 3D and positive 3D being transmitted. Okay, so this should be positive D. Okay, so now that we got the probability of error given negative D, positive D, negative 3D, and positive 3D is transmitted, we can now compute for the total bit error probability of your 4PAM constellation. Okay? So 1/4 here is the probability that your symbol occurs. Since it's equiprobable and there are 4 symbols, then the probability of one symbol being transmitted is 1/4. Okay? 1/2 here corresponds to 1 over B. B is the number of bits per symbol. So simplifying all this, okay, so this is Q of D times square root of 2 over N naught. This is 2Q of D, 2Q of D, and this is Q of D. Then we have this expression for the probability of bit error. Okay? And in terms of EB over N naught, again, we can express D here as a function of the square root of EB. Okay? We can now get the total expression for your probability of error as a function of the signal to noise ratio per bit. Okay? And we get this expression right here. And we want to compare this with 2PAM. Okay? Let's overlay the plot of 2PAM and 4PAM. So as you can see, okay, from this graph, you can actually see which constellation performs better under your SNR. Okay? You can see here that 2PAM is actually better compared to 4PAM. This is related to the minimum distance. If you have greater M, okay, if you have greater M, you have less minimum distance, assuming that the bit energy is constant. Okay, so you can see here that 4PAM is faring worse to 2PAM. Okay, at the same SNR, let's say at 10 dB, okay, the bit error rate for 2PAM is around 5 times 10 to the negative 5. Sorry, 5 times 10 to the negative 6 rather. Okay, the bit error rate for 4PAM at the same SNR right here, okay, and that's around 9 times 10 to the minus 3. So you can see that your probability of bit error is worse for your 4PAM compared to your 2PAM. Okay, so again, the larger the probability of bit error, the worse your performance of your digital communication system. Okay, and it's correlated to the minimum distance. If you have greater minimum distance, you can see that the bit error rate decreases. Okay, there's an inverse correlation between them. Okay, let's look at that more. When we generalize the bit error rate of MPAM, okay, we won't derive it here. I'll just show it to you. The probability of bit error given M symbols and a constellation is equal to this. Okay, so as M increases, the probability of bit error increases, worsening the performance of PAM. Okay, and this is also true. Okay, this is also true for PSK and QAM. Okay, and if you remember the trend for the minimum distance as M increases for PSK, QAM, and PAM, your bit error rate decreases. Your minimum distance decreases as you increase M. So that's why your bit error rate also increases as you increase M for both PSK and QAM. Okay? As EB over N naught increases, as intuitively, the probability of bit error decreases. And it indicates that a larger transmit power performs better at constant noise, which makes sense. If you can't hear someone you are talking to, you tell that person to speak louder. Okay? Because the ambient noise could be large. So if you want to successfully communicate to another person, in a very noisy environment, then you want that person to speak louder, okay, which makes sense. So it also makes sense here that you increase the power of your transmission if there's a lot of noise in the background. Okay? So last note for these expressions, it assumes that a symbol detection error only has one bit error. Okay? And this is only true for high SNR cases. Okay? If you have a large SNR, if you have a small SNR rather, so let's look at it using a 4 PSK constellation. Okay, if your SNR increases, okay, the radius of your possible received symbols also increases. Okay, so if you transmit this symbol, then the possible symbols are in this space. Some parts of that symbol are here. Okay, in the area where your symbol here is not adjacent to this symbol here, but the receiver incorrectly detects this as this symbol. And you have already 2-bit errors in this case, assuming that you're using gray code mapping. Okay, so if you have a low SNR case, this the effect of this crossing this boundary is already not negligible. So in our derivation, the assumption here is that the effect of a 2-bit error for a single symbol error is less likely to occur. Okay, so you need to take note of that when using this expression for a probability of bit error. Okay, normally we simulate it to verify. Okay, so simulation is better than theoretical derivation. Okay, and you will see that in your simulation exercise. Okay, so just to show you, for a 16 PAM, as expected, the bit error rate increases. Sorry, the bit error rate increases compared to your 4 PAM and 2 PAM. Okay, which tells us that if you have high SNR, it's actually better to use your 16 PAM, since increasing M increases the efficiency of your transmission. The same symbol uses more bits. Okay, so if your goal is to have a constant bit error rate, let's say 10 to the negative 4, okay, you can adjust your modulation to have a higher order, okay, to have more symbols if you have high SNR. Okay, so if you have low SNR, then you adjust to another constellation. You can do that if you want to maintain your bit error rate. Okay, the WLAN, the Wi-Fi standard 802.11, actually uses this. Okay, when the SNR is low, it switches to a constellation with a lower number of symbols. Okay, but when the SNR is high, it switches to a constellation with a larger larger number of symbols. Okay, so if the SNR is low, then it can only transmit at a lower bit rate. Okay, but when the SNR is high, you can transmit at a larger bit rate. Okay, if you want to maintain the probability of bit error. Okay, so this is some example of that implementation. Okay, and also to show you, assuming you have 16 symbols, okay, you have 16 symbols in your constellation. This is the comparison between your PAM, PSK, and QAM. So if you recall the minimum distance graph, assuming that EB is constant, remember that QAM has the largest minimum distance for higher number of bits per symbol compared to PSK and PAM. And you can see how it reflects in your bit error rate. Okay? If you have higher minimum distance, you're sure that the bit error rate is smaller compared to symbols with a lower minimum distance. Okay? And this is how you compare the performance of different digital modulation techniques. In general, actually, your different digital communication systems. Okay, when you simulate them, you get a bit error rate, and you can compare your different digital modulation techniques or digital communication systems. Okay, so we're talking about minimum distance here, and there's one example of your digital modulation technique where uh, your minimum distance increases as you increase the number of bits per symbol. That is your FSK. Let's look at the results, the theoretical results, when we increase the number of bits per symbol for your FSK. So it's something like as you would expect, okay? So your FSK decreases, the bit error rate decreases as you increase your number of bits per symbol or your number of symbols in your constellation. As you can see, if you increase the number of your bits per symbol, then the bit error rate of FSK decreases. Okay? So that means if you have a low power, okay, let's assume that we want to transmit with the bit error rate maintained at 10 to the negative 4. Okay? If you are low on power, okay, if you're low on power, then you transmit more symbols for FSK. Okay? Does that make sense? But for PSK, QAM, and PAM, if you have low power, you transmit a lower number of symbols. For FSK, that's not the case. If you're low on power, then transmit more symbols. What are you consuming here? Recall that if you increase the number of symbols for FSK, you're consuming more bandwidth. Okay? At constant data rate. You are consuming more bandwidth for your FSK. Okay? So, basically, it's either you consume more power or more bandwidth to reduce your bit error rate. Okay? And for FSK, if you're limited in power, then you transmit more symbols by consuming more bandwidth. The opposite is true for the other digital modulation techniques. Okay? So just to summarize, we use the BR as a metric to evaluate the performance or robustness of a digital communication system. Normally, we simulate it. There are theoretical derivations, but it's better if you simulate it because for the theoretical derivations, there are some assumptions. Okay? This BR is expressed as a function normally of SNR per bit since the noise affects different modulation schemes differently. So we use the SNR per bit instead so that we have a fair comparison between your different digital modulation schemes. Your BER increases as the SNR per bit decreases. Okay, this is intuitive because if there is less signal power, there's more noise, then you have more error in communication. So BER increases, the number of bits per symbol increases except for FSK. So for PSK, QAM, and PAM, your BER increases, your performance worsens as the number of bits per symbol increases. Okay? So that leads us to the conclusion that if we want to reduce the bit error rate, it's either we consume more power or more bandwidth. Okay? And there are techniques to combine that actually. So the technique that if we use more carriers, more frequency symbols, and using QAM at the same time, a technique that uses that is in the 4G and WLAN standard, we use what we call OFDM. Right? You consume more bandwidth and using more power, you have a more reliable communication system. Okay? So that's reserved for advanced topics, okay? For electives. It's not discussed in the curriculum. Right? So that's the end of this lecture. Our reference here is mainly from Proakis Digital Communications 5th edition. So if you're interested in reading more about this, you can use this reference. Just gonna warn you that it's heavy on the math side. Okay, so if you have any questions or do you want any clarifications, do not hesitate to leave a comment in the comment section below. Thank you for listening. See you next meeting.